In this tutorial, we will be discussing the ideal gas law. The ideal gas law combines the other three laws that we've learned already. Those would be the Boyle's law, Charles' law, and Avogadro's law. It's a general equation, so that way you don't have to memorize all three of them, with volume being proportionate to moles times temperature over pressure. So if we look at the three laws, V1P1 is equal to V2P2. Charles's law being V1 over T1 is equal to V2 over T2. And Avogadro's law being V1 over N1 is equal to V2 over N2. The ideal gas law combines these three laws together. So if you notice V1 over P1, and then if we merge this one into it, it would be V1 over T1. And then if we merge this one into it, we're still talking about volume. Volume is proportionate to the moles now. And if we combine all three of those, you'll see P1 V1 over N1 T1. It's the combined gas law. So here's the Boyle's law, here's Charles's law, and here's Avogadro's law, all in the same equation. And the initial and final relate to one another. When one variable is held constant, the others can be calculated. So in other words, if you know that the amount of atoms isn't going to change, you can disregard that unit. Since the volume of the gas varies with the pressure and temperature, chemists have agreed on a set of conditions to report our measurements so that comparisons are easy. We call these the standard conditions, and you'll see that come up more than once. It's also abbreviated STP. Standard pressure is 1 atmosphere, and standard temperature is 273 Kelvin, which is, of course, 0 degrees Celsius. Once again, the pressure units, there are several different types of pressure units. There's millimeters of mercury, there's torr, there's atmospheres. Make sure that your measurements are balanced out. So let's do a practice one. A gas occupies 10 liters, so that's going to be a volume, at 44.1 psi, that's going to be a pressure, and 27 degrees Celsius, and that's temperature. We automatically know that temperature has to be in Kelvin, so we have to add 273 to this to make it 300 Kelvin. What volume will it occupy at standard conditions? Well, we just learned that standard conditions are 273 Kelvin is the temperature, and then the pressure is 1 atmosphere. Well, since standard pressure is in atmospheres, we need to put this one in atmospheres. So, 44.1 psi over 1. There is 14.69 psi in 1 atmosphere. So we're going to divide that, and that comes out to be 3.00 ATM. So we have V1 is 10.0 liters, P1 is 3.00 atmospheres because we just converted it, and T1 is 300 Kelvin. T2 is 273, P2 is 1 atmosphere. It's asking about the volume. They didn't even mention the moles, so that means it must remain constant. V1P1 over N1 T1 is equal to V2P2 over N2 T2. Alright, they did not mention moles, so I'm not going to even worry about that one. I'm just going to plug the numbers in. It starts off at 10.0 liters at 3 atmospheres. at a temperature of 300 Kelvin. It is then cooled to 273 Kelvin. We're looking for the temperature, or I'm sorry, we're looking for the volume, and we know it's going to be 1 atm. Cross multiply, and then we're going to divide. So that comes out to be 8195.6 atm dot liters over kelvins is equal to 3.00 liters atmospheres kelvins, and we're looking for X. Divide both sides by 3.00. This is supposed to be on top here. Alright, so kelvins cancel, atms cancel, and we're left over with liters. The kelvins, that was a mistake. The kelvins, because it was multiplied, should have been on top. So that comes out to be 27.3, and we're left over with liters. Let's try another one. 28 grams of CO2 is placed in a 30 milliliter balloon, so that's our volume. If the container is warmed from 27 degrees Celsius, so that's T1, at 1.2 atm P1 to 33 degrees Celsius, that's T2, at pressure of 1.6 atmospheres, that's P2, what will be the final volume? So we're looking for V2. Now, since the number of molecules did not change, I'm not even going to worry about the 28 grams. That's just extra information. I could convert it to moles, but the same amount of moles would be at the beginning as at the end. Now, the degrees Celsius, I have to add 273 to it, so that equals 300. And over here, I have to add 273 to this one as well. And that equals 306 kelvins. ATMs are in the same pressure, so I don't have to worry about that. So PV over NT is equal to PV over NT. I don't have to worry about the moles. I just have to worry about everything else. 111222, so that way we show that it changes. Pressure starts at 1.2 atm. That's right here. Volume is 30 milliliters. At a temperature, we need it in Kelvin, so 300 Kelvin, is equal to the final pressure, 1.6, the final temperature, which is 306, that's on the bottom, and we're looking for the final volume. So we're going to multiply these together. We're going to multiply these together. We're going to cross multiply here. That comes out to be 7006.176. The units are atm dot milliliters dot kelvins is equal to 305.28 atm dot Kelvin. Divide both sides. Multiplying this by X because we're looking for volume. Atmospheres cancel out, kelvins cancel out. We're left over with milliliters, and that comes out to be 23 milliliters. So what if the gas isn't actually changing? Well, as we said, P is proportionate to V, N is proportionate to T, and V is proportionate to N. Well, every single one of those had a constant. If you multiplied them together, they were always constant. Well, when we compare them all, we come up with a gas constant. And the gas constant is dependent on what units it is. So it depends on the units of pressure and volume. Notice that moles and kelvins are always the same, so it's only the pressure and the volume that can change. So you always want to make sure that whatever gas constant you're using is matching up to those units. The other gas laws are found in the ideal gas law if two variables are kept constant. This allows us to find one of the variables if we know the other three. So here we are. That's what I said before. If we relate all of them together, it's going to come out to be a constant number each time. And then we end up rearranging the equation so that way it's a little bit less awkward. And it's PV equals nRT. So how many moles, that's going to be our N, are in a basketball with a pressure of 24.3 psi, that's our pressure, volume of 3.24 liters, that's our volume, and 25 degrees Celsius, which is our temperature. One thing to notice the difference between this one and the other ones. And the other ones we had two volumes, two pressures, two temperatures. We always had duplicate units. This one, there are no duplicate units. We have N, P, V, and T. There are no two P's. There's no two V's. So there's nothing changing here. We're looking at a specific instant. What's going to be the amount of moles. And so that's the difference. That's what you want to look for when we're trying to figure out which equation to use. Alright, so P, V, N, R, T are our units, or our variables. With R, that's our constant. That's 0.08206 that we learned on the other slide. And it's atmospheres, liters, moles, kelvins. The reason why I want to put that first is I want to make sure that all my units are matching up to those units. So for instance, volume is 3.24 liters. I have liters here, I have liters here. So it's okay. Pressure is 24.3 psi. Our pressure here is in atmospheres, so I need to convert that to atmospheres. So there's 14.69 psi and 1 atm. And that equals 1.65 atm. Our moles is what we're looking for. And our temperature, we have it in 25 degrees Celsius. We need it in kelvins. So we're going to add 273 to make it 298. Now we can plug these numbers in. 1.65 PV 3.24 is equal to N, which is our X, R, and I know it's a pain to write all these units, but it's really necessary. So that way we can see that it cancels out. Times 298. Alright, notice that the kelvins actually cancel out immediately. The moles will be what we're looking for. So, 1.65 times 3.24 divided by 0.08206 divided by 298 is going to be 0.219. And if we look at the units here, atm, liters, moles, divide this atm, liters, moles. The atms and the liters cancel out. Moles are left over. That's how I know what my units are. We only want two significant figures because of our 25 there. So X is equal to 0.22 moles. We multiply this side, and then divide it. We're going to have one last example. This time we are looking for volume. So P, V, N, R, T. We know our R is 0.08206 ATM, liters, moles, kelvins. So those are the units we want to match up. Our pressure, calculate the volume. We're looking for the volume occupied by 637 grams of SO2. We don't have the number of moles, but we can determine the number of moles by using the molar mass. 637 grams, 64.07 grams are on bottom, 1 mole, so it can cancel. And that comes out to be 9.94 moles. At 6.08 times 10 to the third millimeters of mercury. That's our pressure. Put it over 1. We need it in atmosphere because that's what our units are in for R. That is equal to 8 ATM. And then finally, temperature is negative 23 plus 273, which is equal to 250 Kelvin. Okay, from here, we just plug all our numbers in. So 8.0 ATM times X is equal to 9.94 moles times 0.08206 ATM moles, ATM liters, moles, kelvins, got ahead of myself, 250 Kelvin. Kelvins cancel. That comes out to be 8.0 ATM times X is equal to 203.9 moles ATMs. The moles cancel too, actually. I'll show you that in a minute. Liters over moles. The moles cancel, so we want to solve for X. Divide both sides by 8.0 ATM. 8.0 ATM. ATMs cancel now, and that equals 25.5, and we're left over with only 1 unit of liters. And that explains how to do the ideal gas law.